Good day, everyone. Today we'll be talking about displacement method of analysis using the slope deflection equation. Now, the method differ from moment distribution method, and I will explain how it goes. Now, all structures must satisfy equilibrium equation and the load displacement and compatibility of displacement requirements in order to ensure their safety. That is, they must satisfy the equilibrium equation and all the summation of forces along the x-axis or s-axis, y-axis, and movement must be equal to 0. Now, the displacement method, it requires satisfying the equilibrium equation for the structure. To do this, unknown displacement. Firstly, we must have unknown displacement. Unknown displacements are written in terms of the loads by using the load displacement operation. Then these equations are resolved for displacement. Once the displacements are obtained, the unknown loads are determined from the compatibility equation. Now, let us go to looking at degree of freedom. When a structure is loaded, specified points on it called nodes will undergo unknown displacements. That is, looking at these points, they undergo displacement, and displacements are referred to as this degree of freedom. These displacements are known as degree of freedom. That is to say, their freedom is being displaced, is being affected when there is displacement. Now, in the displacement method of analysis, it is important to specify this degree of freedom. We need to specify them since they have become the unknowns when the method is applied. Now, the number of these unknowns is referred to as the degree in which the structure is kinematically indeterminate. Now, the number of these unknown, it will tell us the degree of its indeterminacy. That is, how many number of unknowns do we have there? If we don't know this angle theta, it might be difficult for us to analyze this structure. So let's proceed and do justice to this problem that we are having here. Now, it says to determine the kinematic indeterminacy, we can imagine that the structure to consist of a series of members connected to nodes, which are usually located at joints and support and at the end of a member. At joint, support, and at the end of members, or where the members have a sudden change in cross section. So we have location 1 at the joint, location 2 at the point, at the support, location 3 at the end of the member, and location 4 at the sudden, where there's a sudden change in the cross section of the material. When we say change in cross section, that is, it's possible for us to have a material made of timber here, and then from here changing it to steel when we talk about the composite material. So that is an example of that. Now, let us look at it says in 3 dimensions, each node of a frame or beam can have at most 3 linear displacements and 3 rotational displacements, and in 2 dimensions, each node can have up to 2 linear displacements and 1 rotational displacement. Now, when we're talking about 3 dimensions, we're talking about the x, y, and z axis, and in that particular case, we can have 3 linear displacements and 3 rotational displacements. But when we're talking about both x and y, that is 2 dimensions, we have just 2 linear displacements and 1 rotational displacement. Now, let us proceed and see what we mean. Let us look at this member. Considering this member here, let's start with this. It's loaded in this form. This is fixed end, and this fixed end, there's no rotation at this end, so we only have rotation at this simply support or this pin support. and this rotation as a angle theta A caused by the application of this particular force here. However, looking at another scenario, let us look at a situation whereby we have two supports A and B, and it's being loaded at point C here. You can see when this member is loaded here, it tends to deflect down in this format, and this, let me say, it travels from here to this particular place, and what it means is that it will create a rotation at this place and another rotation at this place. So the one at A is theta A, while the rotation at B is theta B. However, this theta C too, there's a rotation at theta C, and how do we arrive at that? All we just know is looking at the member like this, where the end of the displacement, then what's the angle that is being displaced, which is theta C, as you can see from what we have here. So let's proceed and let's look at a situation whereby we have a frame structure of this tendency. Let's say we have A, B, C, D as a frame structure fixed as point A and point D. Now if it's been loaded in this form, the structure will tend to tilt towards this direction, and then as it's tilted towards this direction, this one too will try to change its displacement, and then there will be a kind of because of the changing, there will be a kind of displacement and a rotation theta B, and likewise the displacement of C through this distance, and a rotation at this angle theta C, as we have here. See, now let us look at what explanation is written here. We consider some examples beginning with the beam in figure 11A, and we say it's considered P is applied to the beam. We cause the node A only to rotate, while node B is completely restricted from moving, as I explained here. Hence the beam has one unknown degree of rotation, that is only 1 degree of unknown rotation, which is theta A. Now for instance, now for this particular one, how many degree of rotation do we think we have? For this particular scenario, we have 3. We have theta A, theta B, and theta C, and so a vertical displacement delta C. So for this particular one, they say let us look at the beam in figure 11.1b has nodes A, B, and C, and so has 4 degrees of freedom. The whole degree of freedom is 4 altogether. The signature by the rotational displacement, this rotational displacement 1, 2, and 3, and the 4th one is the vertical displacement, which is this vertical displacement theta C. So it is kinematically indeterminate to the 4th degree. Now let us look at figure 11C. If we neglect the axial deformation in the members and arbitrary loading P, as we said, is applied to the frame, it can cause this node B to move through this and node C to also rotate, and these two nodes can be displaced horizontally by an equal amount. The frame therefore has 3 degrees of freedom, which is theta B, theta C, and theta delta B. The frame therefore has 3 degrees of freedom, and thus it is kinematically indeterminate to the 3rd degree. Now let us now look at slope deflection proper, and let's start our analysis. Now this slope deflection was originated by Henry Mandela and Otto Moore for the purpose of studying secondary stresses in trusses in 1915, and we will be looking at this general case. A slope method is so named since it is related to the unknown slopes and deflection of the applied load. Now we want to look at in figure 2, we consider the span AB of a continuous beam. Now it is subject to arbitrary loading and has a constant EI, that is the members, and the member is the same. It's the uniform, let me say the same material rather. Now we wish to relate that the beam internal bend moment MAB and MBA in terms of its 3 degrees of freedom, namely, okay, what we are trying to do is we want to relate this beam with respect to the moment and its degree of freedom. We want to relate everything together, and then we say the moment and angular displacement will be considered positive when they act clockwise. When they act clockwise on the span, we treat them as positive. So now this is the sign convention we're trying to adopt, that when they act clockwise, we take them as positive this time around. Now since the displacement causes the chord of the span and the span chord angle phi to rotate to clockwise, the slope equation can be obtained by using the principle of superposition by considering separately the moments developed at each support, maybe theta A, theta B, and this now, and then the loads. Let us look at how this so let us look at how this equation is being generated. Now, angular displacement at A. Let us consider node A of the member as seen in figure 11.3a. Where is 11.3a? Okay, yeah. Now we are considering this member. We want to consider it to rotate at theta A, while its far end theta B is L fixed. Now, to determine its moment AB that is needed to cause the displacement, we will use the conjugate beam method. Now we have not covered that one. Notice that the end shear at A acts downward. End shear A acts downward, and since theta A is clockwise, the deflection of the beam of the rear beam in figure 3a is to be 0 at A and B, and therefore corresponding moments, sum of moments at each end A and B of the conjugate beam must be 0. Now, what are they trying to say? This is just the derivation of this particular slope deflection equation. What we're trying to do is just similar to what we already know in moment about AB the other time, that we said the moment about when we want to write the stiffness of this particular member, MAB is 4EI theta A over L for the simple support, and we said for the fixed end is half of what we have here, which is 2EI theta A, which is what was written down here. So this particular illustration was derived using the conjugate beam method, and those out of the scope of what we are discussing in this particular one. Now, however, now angular displacement B, if the other time we apply, for this particular scenario, we applied the rotation at this end. This side is support and this side is fixed. However, what of if we fix this side and we apply the simple support here? The same thing applicable. Now this time around, if we do that, what I'm trying to say is that if we have something like this and then we now fix this side and then we place our simple support here, now the displacement we are going to have is something like this, and then we'll have a theta A here, theta B rather, theta B. So now its MBA will now be 4EI theta B over L, while MAB will now be 2EI theta A over L, over B, theta B over L rather. What I'm trying to say is that look at this equation here. We have here what we have here. This one we have it for this particular scenario. We have it moment about from A to B is 4EI over L theta A, because this is where the simple support is, and the fixed support is MBA, and this is the moment which relates to this particular rotation. Now, if we change it the other way, putting this place fixed as I explained here and putting this place as rotation, what we're going to have is similar to this. The only thing is that we have MBA, it will be equal to 4EI over L theta B, and MAB will be 2ei over L theta A. Now let us look at I think it should be, I don't know whether it's written out. Okay, yeah, okay, sorry, it's written out here. You can see if we have it in the other way, this is what we have in this particular scenario. It's just similar to what we have here. The only difference is that instead of the fixed support, to at B the other time, it's applicable at A this time, and then we have the same formula, the same everything. What the difference is that we are considering BA, the starting point, which is where the rotation is 4ei over L theta B, while the other end, fixed end, is 2ei over L theta B. Is the same formula, but you can see the difference is the rotation angle that we're considering for each of these, and this is subject to the support condition that we have ahead the other time. So let me proceed, and now the relative linear displacement if the far node B of the member is displaced relative to A, so that the chord of the member rotates positive displacement, and yet both ends do not rotate, then equal but opposite moment and shear reactions are derived in the member. As before, the moment can be related to the displacement using the conjugate beam method. The conjugate beam is I feel at the end. In this case, since the real beam is fixed support, however, due to displacement of the real beam at B, the moment at the end B prime of the conjugate beam must have a magnitude of theta as indicated. Some moment about B, we have this. So based on the displacement that we had the other time, if it's some moment about point D, it's going to be half of m over ei of the L times 2/3 of this particular illustration comes from what's it called, from our slope, from our conjugate beam method. In that conjugate beam method, though, I think I will need to cover that in another lecture, but for this particular, because that's where we have all this sacred distance and the rest acting, that's where all this one originated from. Now, but I will try and cover that on my lecture on conjugate beam. But for this scenario, what we have is that the displacement, not rotational, the displacement is at AB and BA is equals to minus 6ei over L squared. This is the formula for the displacements referred to the moments. Now, what we're trying to do is that we in slope deflection method, we are trying to look at what is the displacement with in respect to the rotation and the displacement, maybe vertically or horizontally, that we are going to have. And we also make use of the fixed end moment, which is for a simply supported. We, as explained the other time, there's a fixed end moment table which we are going to be adopting. The procedure for this particular calculation is very simple. All you just need to do is look at this is the formula that we are going to be adopting for our slope deflection equation. This formula is the formula for it. So what it means is that there's a general formula, or they can also write it this form too. Now, what it means is that this, if we are considering a member M of A to B, that the moment is equal to 2ei over L into 2 theta A plus theta B minus 3 times displacement over L plus the fixed end moment of that member A to B. And we say fixed end moment, we already know what a fixed end moment is. each member has their own fixed end moment. Let me quickly bring out fixed end moment equation empty table. Hold on. So
it was Chica that did the ground. Then
the fixed end moments. This is the table for fixed end moments. As you can see, depending on the loading condition and the what's it called, if we have a loading where we have point load acting here, the fixed end moment is WL over 8 or PL over 8 for this side and this side. So depending on how we are considering it, so if we say this is positive, then this one will be negative. If we say this is negative, this is positive. That's the way we treat fixed end moment. And now for this particular case, when it is not acting at the centroid, it is PB square A over L square for this end, while this end will be PA square B over L square. So depending on different scenario, this is a sample of the fixed end moment. Now let us look at the formula I have here. Is for this fixed end moment, this is the table we're going to be using for that. So as I was explaining, that the formula for slope deflection is this, which can be symbolized as this also. So we'll go into it, we'll look at it without wasting much of our time. Now let us look at a simple calculation on that. Let's consider having this particular member HBC. Now we want to draw the shear and moment diagram for this beam, and then because of the loading, because of the way it's loaded, we believe that this is fixed end and this is also fixed end. So but at this support we'll be having moment and rotation at this particular support. So we have theta B along this side, moment at BA, moment at B towards C, B towards A, B towards C, and then this moment at C towards B, and this moment about A towards B. Now how do we do this calculation? The first thing is that we calculate our fixed end moment, which is WL over because this is this side is not having any fixed end moment from A to B, it's not having any loading rather from A to B. So the fixed end moment for this particular case from A to B is 0. So that way you are not seeing anything like FEM AB here. Since there's no span, since there's no loading in this particular in that A to B, there's no fixed end moment for A to B. However, from B to C, we have our fixed end moment. I've deleted it. Let me see if I can still paste it back. Okay. Now for the B to C, it's uniformly distributed load and it's loaded in this case. So let us look at the fixed end moment that explains that kind of loading. The one that explains this kind of loading is I think this is the one that is having this kind of loading, either this or maybe this. Now what does it say? It says that the area that is let me say where it's starting from is WS over 30, while the area that is having the highest loading concentration is WS over 20. So that's what we are going to use in this particular case for this. So this is where we have the low support, which is this. So it's WS over 30. Mind you, I told you that if we are selecting negative for this end of this particular support, this side will be positive. So for this one, we are selecting negative WS over 30 for this end. So definitely the other end CB will be positive. So we have WS over 30, which is W is what? W here is 6 kilonewton per meter, and our L is 6 meter. 6 times 6 square over 30 will give us this. Now for CB, we will now have WL square over 20. The W is 6, the L is 6 over 20. But this time around, this is negative, but this is positive. So that's where we got this formula from. So whatever kind of loading we are having, we have to consult the fixed end moment table and select the right value to use. Now let us proceed to the rotation and the unknown. In order to identify the unknown, the elastic curve of the beam is shown in figure 10b, right? Now we already know that it's theta b we are looking for, but let's write the equation out. Now, using the formula that was explained the other time that is, moment about point n is equal to 2e into I over L into 2 theta a, and as this is the fixed end moment. It's the same thing as this, though I always like to this is the equation that we're having, but me, I prefer to write it in this format for myself. There's a way I always write my own. Can I write it out? 3I over L into 2 theta A plus theta B minus 3 phi, then plus fixed end moment of A to B. Why I always like to use A to B, because it makes it easier for me. But for this particular scenario, I will explain what their own case is. What they mean is that when you see N and F, they're talking about maybe the near or the far end, the near end and the far end. So that's what it means in this particular scenario that we have here. So for this particular case here, the 2 theta n is the near end plus theta f of the far end minus 3 displacement symbol here. Now, for this case, let us consider A to B. How do we consider A to B? The A to B for this case is let's say putting the formula 2ei, using this formula that we are having here. Let us now substitute what we have here. 2ei, I is a constant, but the L for A to B, we are considering A to B, please. A to B, the A to B, the span is 8. That's why we have 8 here into bracket 2. Is there any displacement here, or is there any theta A here? No, there's no theta A, so that's why we have 0 here. But is there any displacement at point B, which is theta B? Yes, there is theta B. We left that theta B minus. Now, is there any displacement, maybe movement from towards a distance, maybe upward or downward? Any distance shift, vertical or horizontal distance? No. That's why we have 0 for this displacement here. Now, the fixed end moment, there's no fixed end moment for AB. That's why we have 0 here. So at the end of the day, when we saw what this, it is just EI over 4 theta B that we are left with. The same, however, I want to consider B to A. Now, the same formula, 2E into I. What is L? We have to B to A. The L is still 8. We have this 8. But we have 2, but there is theta B here. So we have 2 theta B. But there's no theta A. That is the far end, which that way we have 0 here. Minus, there's no displacement upward or downward too. That way we have 0 here. So by the time you sum this one together, the fixed end moment for B to A2 is 0, because there's no fixed end moment for this one, because it's not loaded. Now, so we have, by the time we solve this, we have EI over 2 theta B. Now, if you look at this very well, you will realize that what we are having here is that this is twice of what we have here. If you sum twice of if you multiply this one by 2, you have this. So which is exactly what we explained on the moment at the far end, where it is not loaded. Is half of what we have at the near end. So the same thing we have done for A to B and B to A, we will apply the same thing for B towards C. Now, we already know that the fixed end moment for B to C is this, and the fixed end moment for C to B is this. Now, we're going to get our moment for B to C. The same thing now, 2EI over L. But this time around, the L from B to C is 6. That's why we have 6 here, into 2 theta, what B to C, so we are considering this one, theta B first rather, 2 theta B, but theta C, this is fixed end, so there's no displacement here, there's no rotation rather, so that way we are having 0 for this, 0 for this. And then the next thing is that then the next thing is there any vertical shift or vertical displacement, which is there is none here, but if there is, it will be given in distance, so we have 3 times 0. Now the next thing is minus, we know we have plus fixed end moments as we have here. Now this fixed end moment, by the time we add it for B to C, because the fixed end moment is minus 7.2 here, that's what we have here. So by the time you add it, you have this formula. By the time you expand everything, you have this formula for this result for MBC. Now we are going to do the same thing for MCB. Now 2e into I over 6 plus 2, but this time around, when we are considering C towards B, because that what it means is that this side is fixed, this side is unfixed. So theta C will be the first considered, and theta C is 0, right? Theta B is the one in the middle. Now minus 3, there's no displacement here, so but the fixed end moment for C to B is 10.8, so we have the 10.8 here. By the time we solve it together, we have this for C to B. So we proceed to the next step, which is getting the equilibrium equation. Now this is what we're trying to do. From what we have here, we are trying to look at, looking at this joint here, what is happening here should be equal to what is happening here at this joint, because for us to have equilibrium, the summation of moments about this point should be 0. What means that summation of moments from here towards here should be equal to plus summation of moments from here to here should be 0. That's when we can have equilibrium at this point. So what we're going to do is that we will sum MBA plus MBC and make sure it is equal to 0, which is from here our MBA, this is the formula, this is the value for our MBA, which is this particular EI over 2 theta B, and while B to C is this. So using these two, now we are going to sum these two together and have an equation. So let's look at what we have here. Summation of moment about BA and MBC to be equal to 0. So if you sum that those two equations, this is what we are going to get here. So it might be difficult for somebody if he doesn't do it. So let us just do it together. If I sum this and this together, let's say if I sum this plus this equals to 0, so I have EI so if we write it out, we are going to have EI theta B, as you can see from here, EI theta B over 2, that's MBA, this is it here, and MBC, which is this 2 over 3 EI theta B minus 7.2. We are summing them to be equal to 0. That's the MBA plus MBC equals to 0. Now if we expand this, if we add these two together, opening bracket, we have 2 times 2 goes here 3 times this, we have this 3, so we have this so we sum this, which if we take this to this side equal to 7.2. so we have, if we sum these two together, we have 7 EI theta B over 6, which equal to 7.2. Therefore we can say, we can multiply this one by the, we have 3.2 divided by 7 will give us EI theta B, which is equal to 6.7 if we do this calculation. So now this is if we go to this 6.17 EI theta B. So what we just to make, if from here to make theta B the solid formula, theta B equals to 6.17 divided by EI. So that's just what we have here. I don't think I need to write that one also. So that's how this one was arrived at. What we have here, this is how they arrive at it. So I've just done the two calculation explanation there. Now at the end of the day, once we know theta B, we can now substitute the value into this value of theta B into the equation that we have in the initial case, that is MBA equals to EI over 4 times theta B. So what we mean is that instead of EI theta B, now let me say EI theta B, you know, I left my own EI theta B. So let's say EI theta B over 2 equals to MBA. So what I can just say that EI theta B, which is equal to 6.17 divided by 2. So my value is, let me say 3.09. 3.09 is my MBA. So if you look at what we have there, let us look at what we have here. Sorry, no, there's a mix up there. I think I have to write it out. Let me just, okay. MAB is, so don't mind me, MAB is EI theta B over 4. So what it means is that MAB is EI theta B over 4, and my EI theta B is 6.17. So I have 6.17 divided by 4. .17 divided by 4, that should give us 1.54. So my MAB is 1.54. Now if I want to put for MBA will be EI theta B over 2. This is my EI theta B. So I just say 6.17 divided by 2. I think that one is 3.09. 3.0085 or 09. Let's say 3.09. So that's what we should have for while let's look at it. 3.09. Now let us look at what the value of, we have calculated MAB, MBA. Now let's look at MBC, which is equal to 2 over 3 EI theta B minus 7.2. So my EI theta B is 6.17. So if I put 6.17 here, times 2 over 3 times 2 over 3 times 6.17 minus 7.2. So if you point the calculator out, you should have so I should have 4.11 minus 7.2, which equals to minus 7.2 minus 3.08 minus 3.08. So the same thing applicable will do the same thing for this particular expression. So that's how all these values were arrived at. So at the end of the day, we just draw our members and then we put all these moments at each of those points, and then we can determine our reaction at A and our reaction at B. So I think you have done that one in one of your elementary classes. I don't think I should be teaching you how to calculate for reaction at each of those ends. So let me just proceed. I think that is all I need to explain to you on that. If there's any question, don't hesitate to ask me. So this, at the end of the day, we have this particular shear force diagram, and these are bending moments diagram. So if there's any question, you can do your calculation and then you can send your questions to us. Send your questions to me. I will try and attend to your questions. So you can try this example and let's see what you are going to have. Try this particular one. Let's see what you are going to have. Do the calculation. If what you get differ, then let me know so that we can or you can ask me question on the YouTube channel too. So I think that is all for that, and so have a lovely day. Bye.